So today we're going to look at how we can use OpenSees to create a deformation response spectra. We're going to do something similar to here in this textbook, where we take our ground motion, then we take a single degree of freedom oscillator with these properties. So we give it a damping ratio, and we give it a natural period, and we run a ground motion simulation, take the peak deformation, and then we plot this down here. So we'll end up with a plot of peak deformations for an oscillator with a given natural period. Some of the things that we're going to keep in mind is we're going to have to run this a bunch of times, so over a large range of natural periods. So one of the ways to do this, which is quite nice, is to extract our OpenSees models into procedures, which we can call repeatedly. So here I've just got a skeleton made up. So we've got a procedure that's going to create our model for us. It's going to take the natural period and the damping ratio. I've got an apply ground motion procedure, which is going to take a ground motion file, which has our earthquake data in it, and a time step, which tells OpenSees the interval between the points in the ground motion file. I've got a run analysis procedure, which takes the number of steps that we want to analyze and what the time step that we want is. And then finally, the peak deformation procedure is going to tie these all together to run the full analysis, and then it's going to return for us our peak deformation at a given natural frequency, damping ratio, and under a given earthquake. So let's get started in building this out. So first, what we want to do is we want to set our stiffness. We're just going to set it to 1. So what we're doing is we're creating a model which will have a natural period that we're specifying in advance. We want to get the value of pi. TCL doesn't have a built-in for pi, so we're going to calculate it ourselves just using some trig functions. So we want to find 2 times the arcsine of 1. That's going to give us a good value of pi to use. We're going to set our natural frequency to, which is going to be 2 times pi divided by our natural period. We're going to set the mass of our oscillator to achieve our target natural frequency. This is going to take the value of the stiffness divided by the natural frequency squared. And finally, our damping coefficient, which we're going to calculate using 1 times the mass of the structure times the natural frequency times the damping ratio. Okay, so our variables are set. Okay, next we're going to declare our model. We'll use the basic builder model with just 1 dimension. We're going to give it 2 nodes, so the first node is going to be at a position 0, and the second node is going to be at position 1, or 1 meter from the origin. We want to set the mass of node 2. We can use the mass command, but there's also a shorthand way where we can just write in mass here and provide the mass for each degree of freedom. Obviously we only have 1 here, and we're going to refer to the mass here, which we've already calculated. We want to fix our first node, and we want to make sure that our second node is not fixed. Next we're going to apply the material, so let's set up a material tag. We'll use a uniaxial material, elastic material, give it its material tag, give it its stiffness value, and give it its coefficient of damping, which will make sure that our oscillator is damped appropriately. Finally, we're going to create the element. We'll just use a truss element, which is going to have the ID of 1. It's going to go from node 1 to 2. The truss element takes next an area. We're just going to give that 1. And then we're going to have to give it that material tag of the elastic material we defined earlier. Next, for our apply ground motion procedure, we're going to have to set up a time series and a pattern. So let's just create the tags here. So we're going to use a path time series, which is going to take the time series tag. It's going to take a file path. So here we're going to have to give it our ground motion data. I've got the data over here. So if we look up centro.dat, I downloaded this file. And what it's got is a column for the time and then a column for the corresponding ground acceleration. And these are in units of seconds and Gs. So we're going to have to keep this in mind later on. We're going to have to convert it to meters per second. So our file path here doesn't actually want to know about the time. We're going to give it the time separately. So we have to extract this into another file, which I've called elcentro.txt. And this file is just a list of only the second column of the first file, so only our acceleration data. So we'll go back here, and what we could do is put in elcentro.txt. But you can see here we're doing it in a procedure, and I'm just going to give it this gm file variable, which later on we'll set to elcentro.txt. We also need to give it our time step, so that's with the dt flag. Our time steps, as we saw before from our ground motion file, the time step is 0.02 seconds, but again we're just going to keep this as a variable for now. And lastly, a factor. If we leave this out, it's just going to have a factor of 1, so it's not going to scale our acceleration. As I said, we need to convert this into units of meters and seconds, so we're going to give it the constant for gravity. So this is going to convert units in G to meters per second squared. Next, we're going to create the pattern. Here we're using a uniform excitation. We're going to give it a pattern tag. We're going to give it the direction that it acts in. So obviously we only have one dimension, so number 1. But if we had a 2 or a 3-dimensional structure, we would have to give it the appropriate value for the ground motion to be applied in. Next, we give it an acceleration, which comes from our time series that we just created. So that's it for the apply GM procedure. Next, we're going to set up our analysis procedure. So I'll just go through, I'll probably skip through this block while I specify the analysis. Okay, so we've defined what we want OpenSees to use for our analysis. Next, we're going to set up a loop to run our analysis. So we'll just set some variables. We're going to set our time to 0. We're going to set a stable variable. We're going to set our d max, which is what we want eventually. And we're going to set the duration. Here the duration is going to be the number of steps, which we're going to give the procedure, multiplied by the length of the time step. And now we're going to use a while loop to run through and run the analysis across a bunch of time steps. So while stable is still 0, I'll explain that in a second. And we also want to check that our time is less than our value of duration. So once each loop, we're going to update the time and the stable variable. If our model becomes unstable, which means it's not going to return 0, we're going to break out of the while loop. And also once our t is equal to or greater than the duration, we're going to break out of the while loop. So first we're going to analyze, so we're going to set stable to, and then we're going to analyze one time step, and we give it the value of our time step. Next we're going to update our time, so the time is going to be, we're going to use the getTime function from OpenSees. Next, we're going to, for each time step, we're going to get the displacement. So we're going to take the node displacement of node 2 in the first degree of freedom. And what we actually want to do is we don't really care if the displacement's positive or negative. All we're looking for is the maximum. So we're going to put this in an expression where we look for the absolute value of the node displacement. So now what we can do is we'll write a little if statement. So if the value of displacement is greater than our current d max, we're going to set the value of d max to our current d, so we update it every time we encounter a larger displacement. And finally, what we want to do is we want to return the value of d max. Great, so the last thing that we have to do is tie this all together. So it's important that we wipe the analysis so that each time we run it, we're not building our model on top of an already existing model. We're going to set our time step to 0.02. We're going to set the number of steps. Let's have a look at our file. If we go down to the bottom, you can see that we've got 1560 steps in our file. We're going to use the create model function, give it the value of the natural period and the damping ratio. We're going to apply the ground motion. We're going to give it the ground motion file, which is coming in from here, and we're going to give it the time step. Next, we're going to set dmax to the return value of run analysis. So this run analysis procedure is going to spit out our dmax, and we're going to set it in this function, in this procedure. And this is going to take the number of steps and also the time step. And finally, we want to return the value of dmax, which we've just created. Perfect, so we're ready to put this all together. So we can call our peak deformation function. It's going to ask for our natural period, so let's just give it an example value of ½ a second. It's going to ask us for a value of our damping ratio. Let's give it 2% damping. And then we're going to have to give it our lcentro.txt file. If we run this, nothing's going to output for us to see, so let's just print the value that it returns, so this dmax, to the screen. Looks like I've made just a little typo, so lcentro. And another little typo is I've put step instead of steps. And looks like I've made another little typo here. Great, so here we have our peak deformation for our single degree of freedom oscillator with a 0.5 second period and a damping ratio of 2%. We can then run this again. Let's say we want to find out if we change it to a 1 second natural period, and obviously we get a different value. And we can continue running this over a large range of parameters. It's going to get a little bit cumbersome if we keep writing this out and looking at these numbers, so let's write ourselves a little loop to do this automatically for us. So let's set our damping ratio, set our ground motion data file, and we're going to create our for loop. So we're going to take the natural period of 0.01 seconds. We're going to say until this reaches half a second, and each time we're going to increment it by 0.01 seconds. So this little for loop is just going to iterate over different values of Tn. We can see that here if we just quickly run this. So we're going to output 0.01, 0.02 continuously until we hit 0.5 seconds. But what we can do with that is we can run our peak deformation procedure, give it the value of Tn, give it the value of zeta, or our damping ratio, which we've put here, and then give it the value of our ground motion data, which we've put here. So that's just going to run our analysis over this whole range of natural periods. And then we probably want to output it to the screen so we can have a look. And another thing we can do, we can say that our Tn equals Tn, and our Dmax equals this value here. So here we go. That's given it to us over a nice big range. We probably don't want to print it out to the screen like this. What we probably want to do is put it in a file. So we're going to set our file as open. You can call it whatever you want. I'm going to use the results.out file, and we give it the W tag, which means that when it opens this file, it's going to wipe the contents and then write to it until we close the file. And we need to close the file here, so we're going to close output. And this means that every time we run the script, if we run it twice in a row, for example, we're not going to be adding to the end of the file, we're going to wipe it clean and then rewrite it, which is exactly what we want. The puts function, actually, if you only give it a string, it's going to print that straight to the terminal. But we can actually give it a file, so if we give it this output file, we can then ask it for the value of Tn and our value here. I'll just copy that down. And we can run this another time. So we'll see it runs through, prints that output. But if we now visit our results.out file, we can see it's also printed it to a file. We can also tidy this up a little bit. So we only need 2 decimal places for our time. We're going to just take, say, 4 decimal places. Apologies, I should put an F in there for float. We only want 4 decimal places here. I'll just remove this. So when we run, there's no output because I just removed it. But in a second, our results.out will be printed once the program's over. And you can see we've got the first column with our natural period, and the second column is going to show us our peak deformation. Great, so let's copy this whole thing, and we're going to, rather than increasing, we probably want to take until about 3 seconds of natural period, but we don't need this fine grain for the whole time, so we're going to go from 0.5 to 3 seconds, but let's increase this to 0.05 second increments. And we'll run that again. This will take a little bit longer. And here we have the output all the way up to 3 seconds. Here's a little Python script that I've done which is going to read the results.out file and just plot it. So if I run that, here we have our deformation spectra. So we've got our natural period on the x-axis and our displacement on the y-axis. So each of these points is created by running a full OpenSees model within a procedure, and then that's just repeated for a bunch of different values of Tn. Hopefully this demo has been useful for you, and that's all. Thanks.